My name's Melissa Lund, and I'm the 2011 Power One intern for Research and Development. I'm currently a physics student at Cal Poly San Luis Obispo. I actually have only been here with Power One for about 5 weeks now, so I still have a little bit left to my internship, and I still have a lot to learn. But I just wanted to take this opportunity just to give you guys like a brief update on what I've been introduced to since I arrived, what the R&D team has been working on, and where we hope to go in the next couple months. So I'm going to tell you guys about the engineering software that we've been researching. I'm going to introduce a couple design concepts that are underway right now, and I'm going to explain a little bit of the reasoning that we have behind them. So the first order of business when I got here to Power One was researching and choosing our computer analysis software. Now, even all of you who just don't want anything to do with computer programming or just can't stand computer software, I think you actually can appreciate this because it's a really, really cool software that we got. It allows us to input any physical properties that we think might be relevant to our product, thermal properties, tensile strengths, material properties, and it calculates all of those and predicts what's going to happen to our product under certain circumstances, and it's actually fairly accurate. And that's a really amazing thing for us to do before we send the product to production, just to make sure that we foresee any problems that might occur and we can fix them ahead of time. So some of you might be familiar with the software that we're using. We just got all our software licenses. So we're using Pro-E. We just got our SolidWorks license to start doing SolidWorks analysis. And we're actually currently looking into a third software that we think might help us further in smaller details called Autodesk. So one of the engineering concepts that we're actually working on changing the design of right now has to do with our 1.4 megawatt inverter. So I think you can see right here, I don't have a laser pointer, but I'm just going to point. So right here is our 1.4 inverter, and this is a big solar field, and then you can see right there is like a little car driving by. So obviously the 1.4 is for massive scale solar fields, really large roofs. Any customer who has a lot of power to convert is going to look into buying our 1.4 converter. So right now, we're working with the European 1.4 design, and it's kind of a transitional period for us because since our site at Phoenix is so new, we're still very interconnected with the other R&D teams at the other companies, or the other locations of the company. And so this is actually a pretty exciting time because we're starting to sort of transition into becoming an independent group, sort of autonomous, making our own design decisions. Because it's very important, we're trying to shift the market over to North America. And so there's different materials that we need to be concerned with. There's different standards. It's a different environment, so we need to worry about different things. And so eventually we're going to start making our own design decisions based on the environment here in America versus our counterparts in Italy or in Europe. So right now this is the Italian design for the 1.4 megawatt. And so it's actually a pretty crucial time. I think today actually is when they're deliberating on the sort of confirmation for this design. So that's pretty cool. Wish them luck. So I'll just point out a couple of the changes that we're making. As you can see right here in the European design, so this block right here is all the DC components. And so you have all the power from the photovoltaic cells coming in through the DC, going through all the inverter components, and then that block over there is going to be the AC block where it gets the power ready to go out to the grid. So you can see on these new designs, we actually decided that we can incorporate the AC and the DC components into the structural body of the inverter. And the reason for us doing that is it allowed us to make it a lot narrower and a lot smaller, which is just generally more efficient. So as you can see, these are narrowed a ton, and a lot of the components got put in here instead of lopped onto the sides. Another thing that you can see in the original design is these two things up here are some pretty large heat exchangers to help with thermal management. In the new design, we've moved these off of the top for a couple of reasons. First of all, they're just really big. They're really heavy. It's a lot of material and for not quite the best cost. Also, in North America, we have to worry about seismic regulations because there's a lot of earthquakes over here that they don't really have to worry about over there. So we just want to make sure that if there's a massive earthquake or if there's a violent storm, we want our products to stand through those and still have pretty good efficiency when they come out the other side. So R&D also designed a new enclosure for this one. And, oh, just kidding. Help me out, Claudia. So those are a couple of the concepts that are sort of getting underway. So it's a pretty transitional time starting to get these actually put into production and getting on our way. Another thing that my supervisors, Albert and Basil, spoke with me about is other ways we can improve the 1.4 in terms of thermal management. And so, Claudia, I need your help. Hell yeah. So the way that we are managing the cooling and the heating problems with our 1.4 right now is we have insulated walls around the outside. And so one thing that I was asked to look at was just, is this insulation, is it the most effective way to shield our electronics from the weather and from being heated or being cooled? Is it the most cost effective? Does it make the most sense? Maybe it makes the most sense in Italy, but maybe not here in Arizona, where we have much different climate. So I took a look at the insulation. Here's an example of like an insulated wall. I just wanted to show you guys a little bit of the physics behind it. So as you can see from this chart down here, here's the insulated wall right here, and there's a significant drop between the inside of the wall and the outside of the wall. So this is sort of like just a little visual of the heat absorption drop. So it does definitely block the heat flow a lot. But the problem with this is that we need to think about the hot extreme and we need to think about the cold extreme. So if you look, insulation in a cold extreme over here would make sense because you have extreme cold temperatures, maybe sub-zero, coming in from the outside. You want to shield the electronics from that so they can function their best. But the problem with the insulation is if you consider the hot extreme, this is a 1.4 megawatt system. It's producing a lot of heat and a lot of power. And with insulated walls, all that heat is just trapped inside of there. And it doesn't have any way to get out. The external environment is hot also. And so that actually doesn't really make a whole lot of sense if we're trying to keep our electronics cool, which is pretty much what we're concerned with here. So our conclusions for this was that insulation does slow the heat flow, but it's not really the best solution for us. And so one thing that we could do if we wanted to keep the insulation is we could throw an air conditioning in there. That would be very effective. But what we want to look at now is air conditionings. They're complex, they're expensive, they use a lot of energy, and what we want to try and deliberate on is there a simpler, more effective way to do this? Because if we want to have competitive products, they need to be simple. They need to just have good fundamental properties that work well without a lot of extra baggage. And so one way that we can do that is utilizing heat exchange with the external air, which happens naturally. So this is utilizing the convection and airflow to draw heat away from the electronics and into the ambient environment. Benefits of this are it's reliable, it's simple. We can build it right into the structure of our components and not have to bring in any external cooling devices. There's less operational cost, there's less maintenance cost, there's less equipment, there's less size, it reduces the complexity, just makes it a lot simpler. And also, especially since we're in the renewable energy market, a lot of people are concerned with if we have a lot of like refrigerants or coolants or air conditionings that we need to cool down our system, that's going to draw power. And obviously they're running photovoltaic cells, and they don't want to use a lot of power to cool those photovoltaic cells. So, I mean, it's sort of like a win-win, like this doesn't cost us anything, any extra power. So just sort of an example of sort of what I mean by this. So sort of the ideas that we want to utilize. One idea that we had was to have hollow cavity walls and put small vents at the bottom. Hot air naturally goes upward, and so we'd have air coming through the bottom of the vents and running up along the outside of the enclosure and being pushed out at the top by a fan. This way, the air collects the heat from the enclosure and blows all the hot air out so it doesn't affect. Also, another thing that we could do on top of this, inside, if we do sort of counter airflow through the inside of the electronics, it could work on top of this and sort of compound the effect, because we could have the air blowing up through the electronics, drawing the heat away from them, blowing them out the top, and then as it drops down this wall, it transfers all the heat from the air to the outside wall, carrying it out in the same way, but it would just have sort of like a double effect. And so this is just kind of like just an example of the nature of the way that we're going to try and approach things, and just see if we can integrate some of this into our product and just see if we can make it a lot simpler and a lot more efficient. And also outside of this is we would be able to seal our electronics from the ambient air, which is great if we have a lot of dust, which happens in the desert, if there are harsh environmental factors, if there's chemicals, if there's blowing winds, that's definitely a benefit for the protection. So that's pretty much what I've been involved in since I've been here. For the rest of my internship, we're going to continue to be looking at mechanical properties of our inverters, including thermal, structural. We're going to also look at some vibrational properties, and another specific thing is we need to worry about our NEMA 4X standards, which is outdoor standards and earthquake reliability. So that's pretty much it. Thank you for your time. Thanks for being here.